Okay, today we're going to make a transition from the descriptive statistics to the inferential statistics. So everything that we discussed so far in this class, definitions of population and sample, parameters versus statistics. Then we discussed tabular techniques. How do you put a picture on the data, right? Bar charts, histograms. Then we discussed numerical techniques. All of that was descriptive statistics. You have a data set. Please tell me what you see in this data. Characterize the data somehow with just a few of the numerical measures, or just give me a picture. So today we're starting the inferential part, trying to analyze the sample and make some conclusions about what the population may look like, okay, what the parameters may look like. Okay, so inference about the population takes two forms, and we're actually going to look at both of them. That's probably something that you saw already in Math 125, so this part again is a refresher, okay? Supposed to be a refresher. Number one, we'll look at confidence interval, and that's how you estimate the mean or the proportion for the population. So, and then the hypothesis testing, that is something that we're going to be doing actually pretty much the rest of the semester. We're going to test hypotheses in all kinds of different forms, shapes, and sizes. All right, but today our focus is estimation or confidence interval. Okay, numbers got moved somehow. Let me move them back. X bar goes right here. Okay, the objective of estimation or constructing of the confidence interval is to, well, that's what it says, estimate the population parameter, right? And parameter is something that characterizes the population. So for example, if you have numerical continuous data, then the most important, one of the most important measures of the population can be the mean mu for the population. If the data is categorical, remember we discussed that categorical data does not have a mean, and it does not have the measures of variability as well. So for categorical data, the only thing that we can calculate is the proportion, right? For example, let's say voting. In fact, today we're going to take a look at exactly that problem, voting. People voting for a political candidate, and people go to the voting centers, booths, right? They cast their votes, and after that, every vote counts as the one for the Democratic candidate or the one for the Republican candidate. And the only thing that we can compute with these numbers, what proportion of everybody who voted casted their votes for Republican or for a Democrat. Now, we estimate population mean or population proportion based on what we calculate from the sample. So how do we judge what the population mean is? Well, we use sample average, sample statistic, X bar, right? And same thing for the proportion. How do we estimate what percentage of people voted for a Republican candidate? Well, we collect a sample, that's what's called exit poll, and from exit poll we compute in the sample what percentage of people voted for Republican. And from that we judge somehow what will happen in the bigger population if all the votes are counted. Okay? So let's discuss the difference between the interval estimator and the point estimator. So there are two types of estimators. Number one is pointer. Pointer is actually a fairly straightforward thing. I collect a sample. Let's say, let's go back to our old example. I want to make some conclusions about the salaries in the city of Newport News. What's the average salary in the city of Newport News? Well, what do? I don't go for the population data, we discussed that, right? Because it's expensive, time-consuming, unreliable, etc. I do 2,000 people, for example. That's a sample. Let's say from the sample, I compute the sample average, and it turns out to be $42,391. So after that, the easiest thing to do for me is to say, well, that's it. That's the average salary in the Newport News. So I'm going to assume that my sample average is precisely, exactly equal to my population average. That, of course, is not the case, right? So, for example, let's go back to our yesterday's discussion of sampling distribution, okay? So suppose that distribution of salaries, and I don't even need to know the shape, quite honestly, right? Normally, how salaries are in society distributed. We kind of discussed that. Is it normal distribution or is it skewed? It's skewed to the right. Okay, so this is my salaries, right? Individual salaries. Let me try to write it nicely. Salaries. So distribution probably is going to look something like that. Okay, it's going to be highly skewed to the right. All right, and all I have really is sample of 2,000 people. That is it. Okay, so what will happen if I will start taking all possible samples of 2,000 out of my population? Every sample will generate its own average, correct? And if I start plotting the averages on the same histogram, I'll get what type of distribution? Normal, and that's going to be a sampling distribution, right? So if I start taking sample 1, 2,000 people, sample number 2, 2,000 people, and keep doing that until the end of days, okay, all possible samples of 2,000, okay? I can even actually, in statistics, it's called bootstrapping. Bootstrapping is, there are two ways how I can do the sampling. I can take a sample and kind of remove it from the population, right? It's like, for example, what I can do with food cans, cat food cans, right? There is a production line. I take 4 cans, and I open them up, and I measure what's inside. Essentially, I took out 4 cans. They are not part of the population anymore, right? I can't seal them and put back on the conveyor line, right? Not going to happen. But for the salaries, I can go ahead and say, well, let's get a list of everybody who lives in the city of Newport News, and let computer generate 2,000 random numbers, okay? And these 2,000 random numbers is going to be my sample. And then I'm going to generate a second set of 2,000 random numbers. Now, true or false, some of my new random numbers can coincide with random numbers in the previous sample. It can happen, right? It can happen. So therefore, essentially, it looks like I'm sampling, getting a sample, but I'm returning the observations back to the population, and I'm taking second sample as if nothing happened before, right? I forget what I did before. I just say, yep, let's do it again. Some numbers will be the same exact people. Probably not everybody by far, right? But my samples can collect same observations. So in statistics, that type of sampling is called bootstrapping, okay? So if I use the bootstrapping, then I can get how many different samples? Oh my God, astronomically huge number, right? And every time when I get a sample, of course, it generates for me different average, different set of numbers, different average, right? So therefore, the averages for the samples, so here, wow, that is ugly. Okay, hold on. All right, the average salaries will form their own distributions, right? So I take first sample, I calculate first x1 bar, second sample x2 bar. And as I keep taking samples, I calculate more and more and more averages, right? And the averages will form distribution. And just like Phil was saying, this distribution will look not quite like that. It will, hold on. It will look like that, okay? Normal. Why would it look like normal? Do you have an answer? Quick and easy. The distribution, sampling distribution, or distribution of average salaries, will look normal because
the rule, it starts with a C.
The rule? What does the rule say? What's the essence of the rule?
The more samples you take, the more likely it's to become normal.
The higher the sample size, right? Yeah. The higher the sample size, the more normal distribution will look. Remember yesterday when we looked at the animation, there was actually pretty much distribution like that. It was a right skewed distribution, right? So first we took samples of size 4, right? And sampling distribution was skewed to the right. And then we took samples of size like 15. Distribution was still skewed but less obvious, right? And we said, let's take 30. And 30 was pretty normal, right? So when you have 2,000 people in the sample, that is a pretty much guarantee that what you're going to end up with will look like normal distribution, right?
Is that central limit theorem, basically?
Exactly, yeah, central limit theorem. Yeah, in the limit of high sample sizes, the sampling distribution becomes normal. And high sample size, which is 30 or more. Now, of course, the more the merrier, right? So 30 is kind of, that's the bare minimum. So anything above or below 30, we're still not sure what's going to look like. But 30 and more there's a pretty good bet it will look PDN, pretty darn normal, right? In 2000, you're virtually guaranteed to have a normal distribution. Okay, and moreover, what I know is if I calculate my actual mean salary in the city of Newport News, it's going to be exactly same mean as the mean for average salaries, sampling distribution, okay? All right, so now of course I don't get a lot of samples, right? I have only one sample with 2,000 people inside of it, okay? And what is the chance that my sample that I randomly pick, 2,000 people, will be exactly, precisely right here where the mean is located? The chance of that happening is 0, right? Because it's a continuous normal distribution, and we know that for normal distribution, chance of any single value happening purely by accident is 0, because there are infinitely many choices. What does that tell you? That tells you that if I go ahead and collect a sample, and for the sample I compute x bar, there is 0 chance that this is the actual mean mu, right? Because there are infinitely many different possibilities, okay? So chance that I got this precise exact lucky sample that gives me just coincidentally the same exact mean as for the entire city of Newport News, that will never happen, okay? So therefore, how confident I am that my x bar is equal to the mean mu? 0 confidence, right? I know, in fact, that this is not the actual mean. So how statisticians solve this problem? Well, they say, apparently we cannot get, a lucky sample, right? It's very, very highly unlikely. So how about I'm not going to even try to guess the mean of the population as just one single number. Instead of that, I'm going to provide an interval, but my statement is going to be more shady, okay? So instead of saying that, hey, this number is the population mean, I'm going to say, well, let's construct an interval, and our statement is going to be that the true population mean, which we never will find out exactly precisely, is included somewhere inside this interval with certain level of confidence. Okay? And it's not going to be 100% guaranteed thing, right? It's not a 100% done deal, but I'm going to be more confident than 0. And typical values for the confidence are, we discussed them, 90%, standard is 95, and if you want to be really, really rigorous, that is 99, right? 3 different values that statisticians typically use. Okay. All right. Well, this slide basically goes through the same line of arguments, right, that we just discussed. If I get just 1 point, 1 sample, x bar, the chances that I correctly guessed or luckily, calculated exact population average is 0. So I'm not confident in this answer at all, 0 confidence. So in order to become more confident, essentially I take the point and kind of blow it up a little bit into the confidence interval. Confidence interval has 2 boundaries, lower and upper. We call them lower confidence limit, LCL, and upper confidence limit, UCL. Okay. So the estimation of the population parameter, today we're going to apply to 2 different types of problems. We're trying to estimate the population mean in case you have a continuous or interval data, and also in case you are trying to estimate the population proportion. Well, that happens when you have categorical data, nominal or ordinal. And remember, we discussed that statisticians are using Greek letters for the population parameters, right? The mean is called mu, the proportion is called pi. So every time when we're dealing with sample statistics, such as sample average or sample proportion, then we have English characters, right? Sample average is called x bar, and sample proportion is called p hat, but we're going to look at that later today. Okay. Now let me actually switch over back to, this is the part where I'm going to try and explain to you how confidence interval comes to the existence. Okay? All right. But first, let me ask you this question. We used already the knowledge that if sample size is large enough, such as, for example, 2,000 people, then the sampling distribution is going to be normal, right? So we went from the right skew distribution to the symmetric bell-shaped normal distribution. Okay, cool. Also, we used knowledge that the mean of the population and the mean of the sampling distribution are going to be the same. The last piece of the puzzle that I still want to get out of you is, if my population had the standard deviation sigma, what is my standard deviation for the sampling distribution is going to be? That's kind of rule number 3 that we discussed yesterday, right, in the sampling distribution. Remember the formula? What happens with sigma? Is it getting smaller or bigger? Sampling distribution. Smaller, right? How much smaller? So I have to take my old sigma and divide it by, Patrick, do you remember? No? Christian, do you remember? Not quite. Milan? Square root from n, right? Square root from sample size. Okay? That's my rule. All right. And now, let me go ahead and actually, I'm going to use the same picture. Also, in the previous several classes, we discussed that if you have a normal distribution, just like this one that we have on the picture, what happens if you go plus or minus 1 standard deviation to the right? So in other words, I'm going to go to the right, plus 1 times sigma over square root from n, and also minus 1 times sigma over square root from n. Inside these boundaries, what's going to be the percentage of all points? 9, no, not quite. Plus minus 1? 68%, right? 68%. Okay. What happens if I go plus or minus 2 standard deviations away from the mean? So this is minus 2 times sigma over square root from n. And that one is plus 2 times sigma over square root from n. Inside these boundaries, I'm going to have, what percentage of observations? Now it's 95, right? So that would be 95%. And if I go plus or minus 3 standard deviations away from the mean, then inside these boundaries, I'm going to have 99% of all area under the line. Okay? So essentially, what I have to decide pretty much how confident I want to be. Let's say, for example, I want to be 90% confident. Okay? That means that I want to cover the area wide enough to include 90% of all possible x bars, right? If I want to be 95% confident, then roughly speaking, I have to go to the right and to the left about 2 standard deviations, approximately, right? Because that covers the area of 95%, roughly speaking, okay? And if I want to be 99% confident, that means that I have to go plus or minus 3 standard deviations. So, in other words, my confidence interval really defines how many standard deviations to the right and to the left I have to travel from the mean in order to capture more and more and more points, right? So, say for example, I want to be, what's the standard way for the confidence level? Standard value of the confidence level. 95%, right? So let's not be fancy at that point in time. Let's say that my confidence level, and confidence level is 1 minus alpha, right? 1 minus alpha, I want to be 0.95% confident. Therefore, my significance level should be 0.05. Okay? So that means that I have to go pretty much plus or minus 2 standard deviations away from the mean, right? In order to capture 95% of the area under the curve. So that means that if this is my mean that I'm trying to determine, mu for S bars, if I travel, say for example, approximately 2 standard deviations to the right and approximately 2 standard deviations to the left, okay, and I'm going to capture approximately, in these boundaries, I'm going to capture approximately 95% of all S bars, right? Of all sample averages in my distribution of sample averages. But that is also true about the sample average, right? Like the best analogy that I can come up with is if Richmond is 50 miles away from the Newport News, and Newport News is also 50 miles away from Richmond, right? It goes both ways. So how does that help us? Well, here is basically the idea. I'm going to take, let me erase that part. I'm going to take a random sample, just like what I did, okay, in my case. 2,000 people from the city of Newport News. So suppose this is my X bar right here, okay? And I'm operating in the dark, right? I don't know anything about the population, about salaries. I don't know the actual mean. I don't know the standard deviation, nothing. So these 2,000 data points is the only data that I have. That's it, nothing else, right? I have no clue other than that. If I take sample, standard deviation, divide by square root from n, that's going to be kind of an estimate of what maybe my sigma over square root from n is going to look like, right? That's my best estimation of the standard deviation for the sampling distribution, okay? And then I'm going to say, well, just using the same line of argumentation, if Newport News is 50 miles from Richmond, Richmond is 50 miles from Newport News, right? If I go from x bar 2 standard deviations away, 2 times s over square root from n, oops, let it go to the voicemail, right? And same thing happens on the left side. 2 times minus 2 times s over square root from n. Then probably somewhere inside these boundaries I was able to capture the mean, right? Because mean captures 95% of x bars within plus or minus 2 standard deviations, right? If I take one x bar, and if I go from this x bar plus or minus 2 standard deviation, similarly to the mean, capturing x bar captures the mean, right? Within these plus or minus 2 standard deviations. And the chance of that happening is 95%, just like for the mean, right? So that's the idea behind the confidence interval, okay? Confidence interval has the center exactly equal to x bar, as you can see, correct? All right. So therefore, here is what I'm going to do. In order to compute, this is my lower confidence limit, and this is my upper confidence limit, okay? So in order to compute LCL and UCL, all I have to do is take x bar and go certain distance below x bar to get lower, and certain distance above x bar. And that certain distance is called ME, margin of error. Okay, ME, whoops. ME stands for margin of error. Essentially, it tells you what's the uncertainty, right? If I want to be 95% certain, how far should I go to the right and to the left? Plus, minus certain distance, margin of error, okay? So, now, margin of error should be expressed in terms of number of standard deviations, right? So, therefore, in order to compute margin of error, you should have to take a certain number and multiply it by the standard deviation, okay? And standard deviation is s over square root from n. We discussed that, right? The only question is, how do we find out this number? Okay, where does it come from? Well, now let's go back to slides. And statisticians showed some time ago, okay, that if you take a random variable x bar, sampling distribution, right? So the distribution of all possible sample averages. Sample average is the random variable. And subtract the true population mean and divide it by sampling distribution standard deviation as what you compute from the sample divided by the square root from n. This awkward animal is going to be distributed according to the t distribution. It's also called student distribution. Okay, so let's discuss t distribution. T distribution was actually discovered first, introduced by a gentleman called, William Goster, I believe, was his last name. He published a series of papers, in fact, introducing t distribution to the humanity. The gentleman was working for, he was Irish, he was working for Guinness Brewery, okay? And there are a couple of versions, according to Wikipedia anyway. why the student is called, why this distribution is called student distribution. So the other name for this T distribution is also student with capital S, student's distribution. The version number 1 says that since he was working for the company, and that was a for-profit business, they did not allow their employees to publish in journals or articles or newspapers anything that can kind of link back to the company. So therefore, he needed to use a pseudonym. Okay. So therefore, he just chose to sign his papers as student. And version number 2 is he didn't want the competitors to know that Guinness is doing some experimentations with, samples of beer, and they were doing something to improve the quality of beer. So therefore, he published under the nickname student. Well, either way, after he published these papers, signing them student with a capital S, T distribution is called also student's distribution. Okay. So it has nothing to do with students in universities. It's just how the guy signed his papers. Back in 19th century, actually, it was around 1875 or something like that. So we as a humanity, we know students' distribution for about 150 years by now. Okay? Student distribution has this awkward-looking, gigantic, ugly formula, and we don't need to memorize. I just want to put it out there so that you can appreciate the complexity of the subject matter. All right? Student distribution looks a lot like standard normal. So standard normal, remember we discussed standard normal some time ago. It's one special normal distribution, right? With mean equal to exactly 0 and standard deviation equal to precisely 1. Well, student distribution has 0 as the center, so the mean is 0. But the standard deviation actually varies, okay? So student's distribution takes only one parameter. Remember that every distribution takes parameters, right? It varies from distribution to distribution what kind of parameters distribution is taking. For example, let me ask you this question. Normal distribution, how many parameters do I need to fully get the shape of the normal distribution and the location? How many parameters the normal distribution takes? We discussed that, right? Yesterday or a couple of days ago.
Say the question again.
How many parameters the normal distribution takes? 1?
2.
Yep, 2. 1 tells you where the center is. Another tells you how wide it is, right? That's the standard deviation. How many parameters the binomial distribution takes? It's also 2. One of them is number of trials, and another is probability of success on each trial, right? Poisson distribution, we didn't discuss that in details, but it takes only one parameter, the average rate of customer arrivals, okay? Student distribution also takes only one parameter, okay? And this one parameter is called number of degrees of freedom, and Greek letter nu is used, okay, for number of degrees of freedom. So the variance of the standard, of the T distribution can be computed using that formula. Number of degrees of freedom divided by number of degrees of freedom minus 2. And obviously it works for nu greater than 2, because if it's equal to 2, then we have division by 0, and that's not a good thing in math, right? Okay, so let's actually discuss briefly. Let me go to the next page. What happens, so variance of the T distribution is given by this formula, nu divided by nu minus 2. Also, kind of linked to the sampling, okay? Every time when you take a sample of the size n, that was shown by the same gentleman, Mr. William Gossett, I believe was his last name. If you take a sample of size n, then you should use a T distribution with degrees of freedom, df, or the same thing, nu, equals to n minus 1. Okay? That's the rule, basically. So the larger the sample size, the more degrees of freedom you're supposed to use. That's the bottom line. And let's take a look at what happens with variance. Okay? So the variance of the T distribution is equal to nu, which is n minus 1, divided by nu minus 2, n minus 1 minus 2, or n minus 1 divided by n minus 3. So what happens if I start taking larger and larger and larger samples? What happens to my variance? Well, let's say I'm taking sample of the size 50. Okay? Then my variance is equal to 49 divided by 47. Correct? So it's going to be 1.00 something, right? Well, let's say 1.03. I don't know if this is right or not, but let's just say. What happens if my sample size is equal to 500? Then I'm dealing with 499 divided by 497, right? And it's a much closer number to 1 than the previous one, right? So it's going to be something like 0.0002 or something like that, okay? What if I take 5,000? Then you're dealing with 4,999 divided by 4,997. And that's very close to 1, right? So what happens if n goes to plus infinity? If n goes to plus infinity, the variance goes to 1. And therefore standard deviation goes to also 1, right? Because standard deviation is the square root from the variance. So see what happens? As I get larger and larger and larger samples, the standard deviation approaches to 1 and the center is 0. So your t-distribution starts to look more and more and more like standard normal, right? So in the limit of large sample sizes, your t-distribution becomes standard normal, okay? So how is that relevant? Well, here, let me show you the previous notes. This one probably, no. This one, okay. Remember we discussed that in order to find out lower and upper confidence limits, all I have to do is take x bar, which is right in the middle of my confidence interval, and go plus or minus margin of error, right? And how to compute margin of error is very simple. You have to take your standard deviation and multiply by number of standard deviations that you want to go to the right and to the left. So the main question here remains is, how do we compute that number, right? And it's actually very easy. So let me show that on the new picture. So let's say that this is my t-distribution. Let's say I'm getting a sample with n items in it. N is my sample size. That immediately tells me that this is the t-distribution, which looks like that. No, not quite. Which looks like that. T-distribution with degrees of freedom equals to n minus 1. And the center is 0. Okay? In order to find out number of degrees of freedom, in order to find out how many standard deviations I want to go to the right and to the left, first thing is I want to decide for myself what confidence level I want to pick. So I have to say myself 1 minus alpha is how confident I want to be. Let's say it's 0.95. So therefore, the likelihood of an error, the chance that I will make an error or significance level is going to be only 5%. Okay? So here's the deal, ladies and gentlemen. I want to go to the right and to the left a certain number, certain distance, right? So that's going to be a value of t with n minus 1 degrees of freedom. And because of the symmetry, that's going to be negative same number, right? Because it's a symmetric thing with n minus 1 degrees of freedom, such that in between these two boundaries, I'm going to have area exactly 1 minus alpha. That's my confidence level. And outside of these limits, I'm going to have whatever is left. So that's my significance level, but because I have two tails, right and left, I have to split it in half, right? So that's going to be my significance over 2, and that one is going to be my significance over 2. Okay? So really what I need to find is this value right there, okay? I need to find the value of t variable with n minus 1 degrees of freedom, which gives me in the right tail significance level over 2. Small area. Okay? And obviously, on the other end of spectrum, I'm going to have exactly the same value, alpha by t with n minus 1 degrees of freedom, alpha by 2 in the right tail, but with a minus sign because it's a symmetric distribution, right? And that will give me how many standard deviations I want to go back to the left or forward to the right. So in other words, to summarize, okay? In order to compute upper confidence limit and lower confidence limit, all I have to do is take my sample and calculate sample average, right? And then I have to say, well, for upper, you have to go up. For lower, you have to go down. How many standard deviations? Exactly that number, okay? T value with n minus 1 degrees of freedom, which gives me alpha by 2 in the right tail, and multiply by the standard deviation, and that is it. And that part, by the way, is called what? We discussed that. Plus or minus certain value? Margin of error, right? So this is margin of error. And that's how you compute the confidence interval, ladies and gentlemen, okay? Do you want to give it a practical spin? That's a bunch of theory, right? But at the end of the day, we need to know how to apply this knowledge. So, let's give it a practical spin now, okay? All right. Now, for that, I actually have a problem. So let me scroll down to the problem. Problem is right there. FedEx. So, let me tell you a fascinating story about FedEx, how FedEx works, okay? What happens if you send a package for Christmas to your grandma in Fresno, California from Newport News, Virginia? Well, of course, you get the package, put it in the box, and go to the FedEx office, right? You give it to them. What happens to the package next? What do you think? Yeah, where do they move it? No, not directly.
They move it a little bit, and then a little bit, and then a little bit.
Not quite. They operate something that's called hub and spoke system. Okay, so the idea, and a lot of airlines operate this way, by the way. Hub and spoke system means that they have central location, a hub, and all packages come to the central location. Or most of them, not all of them. So if you send, for example, package from Newport News to Norfolk, that's probably going to move directly, right? Because the distance is very short. But if it goes from Newport News to Fresno, California, there is a good bet that they will drive it to the airport, nearest airport, probably in Norfolk, okay? And then they use the FedEx plane to fly it in corporate headquarters city, which is what? Where are the corporate headquarters for FedEx?
It's Kentucky, Louis.
Memphis, Tennessee.
It's UPS in the plane.
Mm-hmm.
Yeah, that's true.
Yeah. FedEx is in Memphis, Tennessee. So they fly package to Memphis, every package. Doesn't matter if it goes from Newport News to Fresno or from New York to Arizona, Tucson, Arizona. So the package goes to hub in Memphis, Tennessee, and they in fact call it super hub because it's the biggest hub that they have. It's the size, I forgot how many, it's like a block of the city, really. So it's like 5-minute driving past this place. Okay, so it's huge. That's their sorting facility. So all packages that fly to Memphis, Tennessee, they get delivered, and it's right next door to the airport, obviously, right? So, and all of them are being sorted semi-automatically. They have software and a bunch of conveyor belts, and people who basically, push packages in and out of conveyor belts, and so they sort, all packages are being flown to Memphis, Tennessee, and then after that they're placed on the outgoing planes. So all packages that go to San Francisco area, they're put on the same plane that flies over to San Francisco, okay? And then they unload it in San Francisco and distribute locally, okay? So that's something that's called hub and spoke system. By the way, a lot of airlines operate the same way. An example would be Delta that we talked about, right, today at the exam. Delta, where is the corporate headquarters for Delta Airlines? It's in Atlanta. Yeah. So if you're flying Delta, then chance is that your connection flight is going to be in Atlanta. So sometimes even to fly to, for example, I don't know, if you want to fly from Richmond to, let's say, Austin, Texas, using Delta, there is a good bet that you will fly to Atlanta first, and then from Atlanta to Fort Worth, Dallas, and then from there to Austin, Texas, maybe. But that's where a lot of connections are being made. So same idea, hub and spoke system. Well, anyhow, FedEx, true or false? FedEx operates in a highly seasonal business where they have peak demand and when they have low demand. True. When the peak demand happens? Christmas time, right? When people send a lot of useless stuff to each other, right? That's basically their busiest season. And FedEx relies heavily on UPS, the same thing, by the way, right? they rely heavily on temporary workers. Now, the problem with temporary workers is, they call on students, so because students are very flexible, right? Problem with temporary workers is they're not quite as effective as seasoned professionals. They worked several years at FedEx, right? So in terms of sorting packages, they need to go through some sort of training. So here is a human resource management, essentially, problem, okay? FedEx developed their training program where they hire a fresh employee temporarily, and they put them through the 1-week training program, how to sort packages and not get fatigued and not lose the focus, all these things. So seasoned professional can handle on average 500 packages per hour, okay? So can a new worker achieve the productivity close of at least 450 packages per hour within 1 week of being trained? Now, the truth is, not every person is the same, right? If they hire me, I may handle, 350 maybe packages, right? If they hire Phil is much quicker than me, so he will handle 600 packages. That doesn't mean that I'm sharper and have more concentration. Probably it's the other way around. So different people, of course, have different abilities, right? But they want to evaluate how they're doing in their training program. So 50 workers were hired and evaluated. So they went through 1-week training program, and after that FedEx said, okay, let's put them on the conveyor belt and let's see how they do. So they track them for 1 hour and record how many packages every single person out of this 50 sample size can handle per 1 hour. Okay? And here is the punchline, right? Given the data, can we claim that workers reach the productivity of at least 450? That means 450 or more, right? But not less than that. Within 1 week of being trained and hired. Okay, so let's open up the data. There it is. I actually uploaded that yesterday. So if you go to Scholar, you will see jump data sets, and closer to the bottom you will see fedex.jump. So let's take a look at FedEx. So jump, download that and open it up. And there it is. Okay, so first things first. I want to get some information out of this data, right? What are the two things that I can compute that will help me to build the confidence interval? Well, one is X bar, right? X bar must be in the center of the confidence interval, right? From X bar I go to the left and to the right, same distance. Number two is standard deviation, right? These two things I need. Okay, so let's get the statistics summary. And let's get the distribution, just for the heck of it. Well, actually, we're going to use that. So I go to the distribution, that's what we used, right, so far. Get the packages, and then click OK. And again, let me turn it around, show in the stacked form. Here is my distribution. Okay? So, a couple of things that I need are mean, 454.54, and my standard deviation, right there, 33. So let me write them down. 454.54. So I'm going to open a new one. X bar 454.54, and the standard deviation for the sample, right? I don't know anything about the population, so I'm not using sigma or mu. I'm trying to estimate them, right? So this is what I know from my sample, 33 point something 0782. 0782. Well, first of all, this is a point estimate. Agree? This is what I'm getting from the sample. So if I'm a simplistic guy, I can say, well, the question of the problem is, do my employees achieve at least 450 packages per hour of productivity? Oh, I'm looking at X bar, so this is the only thing that I have, so I'm going to say that, okay, suppose this is my actual mean, mu. And if that is the case, then they certainly do achieve higher productivity than my target, 450, right? So my training program is doing just fine. I have no issues. I should keep doing this training program because this is where I want to be, okay? How confident am I in this answer? That this is actual mean. 0% confident, right? So therefore, Now I want to become a little bit more confident. Okay, so let's say that we're going to use standard level, right? 1 minus alpha 0.95. I want to be 95% confident. So that means that in order to create the upper and lower confidence limit, I have to find out the value of t, right? That has, oh, by the way, let's collect some other information. What's my sample size? 50, right? Okay, so my sample size n is equal to 50 people. So therefore, what's the number of degrees of freedom that I'm going to use? Nu or df, degrees of freedom?
Did you record this?
Mm-hmm. Yeah, I believe it's recorded. Let me double check. Doesn't show me for some reason, but yeah, I'm fairly sure it's recorded. What's the number of degrees of freedom that I'm trying to achieve? Oh, that I have to use? It's n minus 1, 49. Yep, 49 degrees of freedom. And this is my t distribution, right? T distribution with 49 degrees of freedom. And this is 0, the mean. So if I want to use a 95.95 confidence level, that means that in the right tail I should have 0.025. That's exactly right. So 0.05 divided by 2, that should be 0.025, right? 2.5% should be the area in the right tail of the t distribution. And exactly the same thing, 0.025 should be the area in the left tail of the t distribution, right? So that should give me t with 49 degrees of freedom, 0.025 in the right tail. That's how many standard deviations I should travel to the right and to the left in order to get the margin of error. Okay? So first thing, what I'm going to show you is, again, how to go through pain and suffering and manual calculations, okay, and to compute the margin of error, upper and lower confidence level. And then we're going to see where to find that in JUMP. JUMP, in fact, already computed that for us, okay? We're just going to compare if our computations are exactly the same as what JUMP offers, okay? All right, but I'm going to go back and let me put that down. Let's find the t value, right? So for that, we need to use the distribution calculator. So go to help and sample data. And over here, we need to go into teaching scripts, interactive teaching modules, and distribution calculator. So that's not normal distribution that I need to use, right? But in the list, I have to choose the t distribution, students distribution. Parameters, df stands for degrees of freedom, and that should be 50 minus 1, that is 49, right? And I'm looking in the right tail, x greater than q. First of all, I have to switch, right? Because it gives me values and then calculates the probability. I'm actually doing the opposite, right? Input probability and compute the value. And that should be a right tail probability. Well, it doesn't really matter. I can either say to tail and use 0.05. Let's do that. To tail and use 0.05. So therefore, here is my t with a plus sign, and here is my t with a minus sign, right? Or I can say right tail only, and in this case, just like Christian told me, 0.025, right? Half of that. And that gives me exactly the same thing. Okay? Now, remember we discussed that plus or minus 2 standard deviations away from the mean gives you 95%, right? So we choose to use 95% confidence. So therefore, number of standard deviations should be approximately 2, right? Is it? Value is 2.0096. So what we kind of guessed before that, yeah, 95%. 2 standard deviations gives you 95%. So that's consistent, right? It says the number of standard deviations close to 2.0096. That gives you 95% of the area. That corresponds to the to the confidence that I'm using, 95%. So that's actually a nice coincidence here, right? Okay, so going back to my notes, right there. This value, t, 49 degrees of freedom, that gives me 0.025 in the right tail, is 2.0096. That's the one that I have to use. And now I have all the necessary ingredients for my secret ingredient soup, right? Like in Kung Fu Panda. So first let's compute the margin of error, okay? Margin of error, ME. That's going to be t with 49 degrees of freedom, 0.025 in the right tail. And that should be multiplied by my standard deviation over the square root from n. Right? So t is 2.0096. Standard deviation is right here. 33, that's times, that's not plus. 33.0782 divided by the square root from what number? 50. Yep. Oops, what happened? What did I do? Okay, divided by the square root from 50. Okay. Now that part, unfortunately, I cannot do inside my brain. So I have to call on a big fat calculator, which is Excel. Right? So t value multiplied by sigma, not sigma s, divided by the square root from the n. Okay, so let's start Excel. Again, this is long and difficult way, okay? When we're done with long and difficult way and get the answer, I'll show you where is that answer in JUMP. So what we do during like last 20 minutes or so, JUMP does that in one click, okay? So margin of error, ME, equals my t value 2.0096 multiplied by my s, 33.07, I forgot what it is. Let's see, it's right here. 33.078268. 0.78268, and divide that by square root. That's how Excel calculates the square root function called sqrt from 50. And here's my margin of error, 9.400. Okay. So after that, this is my margin of error. So let's compute upper confidence limit and lower confidence limit. All right, but first I need to go back. Oh, I believe I remember. My x bar, the average for the sample is 454.54. I remember because there's a lot of 5.4s in it. Okay, so remember how to compute upper limit. I have to take my x bar and add to that margin of error, right? This number. X bar plus the margin of error. And same thing happens with the lower confidence limit, but with a minus sign. I have to take x bar and subtract the confidence, the margin of error. Okay. So 445.1391 and 463.94. Well, now let's compare. Okay, I'm going to make it smaller. So when I did the analysis of my sample in JUMP, it gave me histogram, it gave me different quartiles, standard values, and summary statistics. And part of summary statistics is upper 95% and lower 95%. Are they the same value or are they different values? Let's take a look. 463.94, that's your upper, and 445.139. Close. Yep, close enough. So the difference only in like 4 decimal, right? So why do I do that? Well, number one is I want you to learn the principles behind it. What happens? So this is not black magic, okay? There are formulas. So this is pretty much the mechanics of computations, right? Of upper and lower confidence limits. All right? And homework that I am going to assign today includes one problem very similar to this one. Okay? So do you want to take a 10-minute break? And then we'll continue? All right. Okay, now let's discuss how the confidence interval affected by manipulations with sample size and also with confidence level. Let me go back to the formula. Okay, here is the formula, right? Margin of error essentially tells you how far you go from x bar to the right and to the left to calculate the limits of your confidence interval, right? And, well, first things first, let's take a look at S. S is the standard deviation of the sample, right? Let me ask you this question. Do I have a control over the standard deviation of the sample? No, I don't, right? Whatever comes out, right? So people, different people have different productivity, right? FedEx hires them. There is variability among them, right? One guy is slow, another guy is fast, the third guy is in the middle. It is what it is, right? So whatever comes out of sample as the standard deviation, I cannot change that. That's just human nature, right, in this specific example. So this number I should treat as given to me, that I have no influence on this number, right? Do I control the sample size? Yes, I do, right? In this case, I chose to get larger sample. Oh, the sample of 50 people, right? Can I get more people in the sample? I sure can. I can get extra 50, extra 100, etc., etc. So this thing I control, right? And so let me ask you this question. What happens if I select larger sample? What happens with my margin of error? According to this formula. Goes down, right? Because sample size is larger, square root is larger, I divide by a larger number, I get smaller margin of error. So which means that the larger the sample that I collect, the smaller my confidence interval is going to be, right? So one way how you can manipulate the accuracy of your results, say for example, I want to stay 95% confident, right? So this 95% part, that doesn't change, okay? But still, it's plus or minus, what did we compute? 9 point something, 9.4 was it? Margin of error? Plus or minus 9.4, right? What if I don't want to change my confidence level, but I want the confidence interval to shrink a little bit more? Well, I can just go ahead and collect additional samples, increase my sample size, and that will shrink the confidence interval, agree? Now, arguably, that will also change somewhat the standard deviation, correct? Because more observations, more numbers, different results, right? But probably it's not going to move that significantly. Standard deviation probably is not going to be affected hugely, okay? So one way how you can control the accuracy of your conclusions, how wide your confidence interval is to manipulate, decide how many observations you want to include in your sample. That's another thing. So n goes up, margin of error shrinks, right? Confidence interval shrinks. Now, let's also discuss how my confidence interval affects the margin of error. So, what if I want to go from 0.95 confidence to 0.99? Will it make confidence interval larger or smaller if I'm keeping sample size the same?
Instead of 0.99?
Yeah, instead of 0.95, I go to 0.99. It's going to be larger or smaller? Smaller or larger?
More confident it would be smaller.
More confident, it's going to be smaller. All right, let's see. So let me just use this graph, okay? So 0.95 was the area in the middle, right? And 0.0 to 5, another 0.0 to 5 was the area in the tails. So what if I want to increase my confidence from 95 to 99%? That means that the area is getting larger, right?
Yeah, but on the tails it's smaller.
No, on the tails it's smaller.
No.
Absolutely, yes. On the tail it's getting smaller, but the area in the middle is getting larger, right? So what happens with the value t? It goes from here to here, agree? So that means that number of standard deviations, so essentially this value, right? My t value, it increases, right? So I take the standard deviation, this part, multiplied by a larger number, I get higher margin of error, right? So if I want to be more confident with in my answer, from 95% to 99%, I need to use larger t score, and that makes margin of error larger, and that makes the confidence interval larger, right? So therefore, the more confident I am, the wider is the spectrum of values that I have to look at, right? My confidence interval gets higher. So what if I want to be 100% confident? Can I be 100% confident? No, right? For that, I need to move my t-value, this one, where exactly? All the way out there to plus infinity, right? Then I'll get, because this is infinite distribution, right? So if I want to be 100% confident, so that the area in these boundaries is equal to 1.0, I need to move boundaries to minus and plus infinity. And after that, my t becomes plus or minus infinity, and my margin of error becomes infinitely large, right? And my confidence interval becomes from minus to plus infinity. So it's going to be like simple statement that I'm 100% sure that my true population mean is somewhere between minus and plus infinity. Well, duh. As if it wasn't clear from the get-go, right? So you cannot be 100% sure, pretty much. That's what I'm trying to emphasize. Another way around it works as well, by the way. What if I want to go from 95 to 0.90 to 90% only? So that means that my confidence interval uses lower value of t, right? So t moves closer to 0, right? It's a smaller value. And therefore, in my margin of error formula, I'm using smaller value for t score, and therefore my margin of error is getting smaller, right? And therefore confidence interval shrinks. What if I want to be 0% confident? Let's consider an extreme case. 0% confident means, where is my t value? It's going to be right there in the middle, right? So if t equals to 0, if I'm right there in the middle, then the t equals to 0, so that part equals to 0. How much is my margin of error? 0. And my confidence interval becomes x bar plus or minus 0 or x bar. And that, we're back to the point estimate, right? Remember when we started, we said point estimate is what I evaluate the mean to be, but I'm 0% confident. And yes, in fact, it is the case. If I'm 0% confident, my t equals to 0, margin of error shrinks to 0, and your confidence interval collapses into one only point, correct? Okay, and let me show you how to manipulate the margin, the confidence level in JUMP. So right now, by default, it shows us 95% confidence interval, because as we discussed, 95% confidence, 5 significance, are the standard values in statistics, right? So if I go to summary statistics, the red triangle right above it, and say customize my summary statistics. At the bottom, you will see enter 1 minus alpha for the confidence interval, right? And right now it's 0.95. That's what it's showing by default. Let's say I want to be more confident, 0.99. We just discussed this will result in wider limits, right? Well, let's see. If I click on the OK button, it updates the numbers and it says upper limit, it was 463, I believe, right? And now it's 467, so upper limit went up. And lower boundary was 4, oh gosh, what was it? Remember? 4, no, I believe it was the original 445. Oh, yeah, yeah, you're right, 445, you're right, 445. But was lower boundary, and now it's 442. So upper limit went up, lower limit went down, right? So, as we discussed, the confidence interval got wider, right?
What is the inter-trim mean percent? Is that needed?
In the settings?
Yeah.
Oh, that part I don't know, quite honestly.
So we don't need that.
Yeah, we're not going to use it. By the way, my original question, right? It's important to keep kind of your, your eyes on the ball, right, and not to lose the sight of the forest behind the trees. So we were computing all these upper and lower limits, and that's fine. But the question that was asked originally: do we run an effective program, right? And based on X bar, it looked that way because X bar was 454, right?
So within that range.
Yeah, so 454 is more than 450. Therefore, we said, well, yeah, based on X bar, it's an effective program, but we're not confident, right? Because it's just X bar. Now we're 99% confident, okay? Now, with 99% confidence level, let's take a look at what happens. My upper limit is at 467, which is more than 450. That's what I'm shooting for, right? But my lower limit is at 442, which is below the 450, right? What I'm shooting for. So, now, can I claim that my X bar, or that my mean productivity of workers is actually greater than 450? Let's make a graphical argument, okay? So here is the deal, right? This is my golden standard, mean equal to 450, question mark, because I don't know, right? My X bar was right here. It was on the high side. It was 454.54. And that made me happy, right? So I was saying, yeah, X bar is great and everything is nice. But I was 0% confident in this answer, correct? Now I constructed a 99% confidence interval, right? 99%. Let's call it CI for abbreviation purposes, confidence interval. And my CI goes from 442, if I remember correctly, let's go back, 442, right, until 467. So this is my lower confidence limit until right here, 400 and that's right here, 467, and that's my upper confidence limit, okay? How do I interpret my confidence interval? I'm going to say, whatever the mean is, it's a big mystery to me. I will never find out the mean, because to find out the true mean, I have to perform gigantic volume of computations, right? Or data collection, right? So I'm not going to even try. So whatever the true mean is, forget it. I'm not getting it ever, okay? All I have to do is try to evaluate where the mean can potentially be. And with 99% confidence, I was able to conclude that the mean is somewhere between these two boundaries, 442 and 467. Well, note that the cutoff for me between the effective program and ineffective program, 450, is somewhere inside my confidence interval. So this portion of my confidence interval tells me that the program is yay, right? And that portion of the confidence interval tells me that the program is nay. So this is yay, and this is nay, okay? So can I conclude confidently that the program is a success? No, right? Because my confidence interval implies that it may be actually on the other side of the fence, right? It may not be quite at the target that I'm shooting for, okay? If this is 450, and if my entire confidence interval is above, okay? So this is my lower confidence limit, and this is my upper confidence limit, and the entire confidence interval is greater than 450, then I will say yes. Then I would say, yep, 99% confident that program is a success. They achieve 450, actually more than that, okay? If the entire confidence interval is below, on the other hand, lower confidence limit and upper confidence limit, okay, if the entire confidence limit is below, then I would say, nope, certainly not. I'm almost there, but not quite, because 99% confident that mean is somewhere here, and it's not quite 450. But I'm in this situation, right, where part of the confidence interval tells me that, yes, you are in a good shape. Another part tells me, nope, you're not in a good shape. So therefore, this sample is inconclusive. So what I was was inclined to believe based on my X bar seems to be not quite the case when I'm getting more confident, okay? So here is what I always tell students in statistics class. Do not believe your eyes, okay? What you see from X bar is just a point estimate. It's just one sample. That's it, okay? In order to gain more confidence, you need to build confidence interval and see what it tells you. So this confidence interval tells me that it's not quite success yet. We don't know. Maybe yes, maybe no. It's inconclusive. We can't say. All right? Now, the last thing that I wanted to illustrate is kind of statistical meaning of the confidence interval. See, what we did is we constructed just one confidence interval, and there is a 99% chance that it captured the mean, and there is only 1% chance that it's out, right? In spite of our best efforts. How can that be the case? Well, here. Okay, here's my sampling distribution. Here's my sampling distribution. Okay, let's say this is the average, 450. And this is distribution of all possible sample averages. Okay, so sometimes, most of the time, I get all X bars somewhere in the vicinity of my mean, right? And then I take X bar. This is my X bar, for example. Okay, this one is my X bar. And I create margin of error, and I go to the right and to the left, and in DD I capture the mean. It's right here, okay? Then sometimes I'm getting the sample right here, okay? This is my X bar. And I go again, margin of error to the right, to the left, and I capture the mean. But every once in a while, I get bad sample, right? Unlucky sample, which is far away. Say, for example, it's right here. This is my x bar. Too high. Okay? And I go to the left margin of error, to the right margin of error, and this is my true mean, but I did not capture it, right? It's still outside. So therefore, statistically, you can think of that this way. If I build 100 confidence intervals, right? Then if I'm using 99% confidence level, approximately 99 of them out of this 100 will capture the mean, right? Somewhere. And one of them will miss it, right? It will be too far on the right or too far on the left. And here I want to illustrate that concept with the demonstration from Students Brown University right here, okay? I showed you this site before, right? Seeing statistics. Okay, so statistical inference right there. Under construction, but that's okay. I tried it yesterday and it did actually work. So let's say that my choose probability distribution to sample from. So that basically says that let's use normal distribution as our population distribution, okay? And let's do sample size of, I don't know, 30, and the confidence level of 95. Yeah, 95, okay? Start sampling. And you can see that I'm getting samples, right? Every sample generates the average, that's the green dot. And what do you think are the lines to the right and to the left? That is your margin of error. So essentially, what these things represent, every one of them is the confidence interval. What do you think greens represent? Greens are the ones where we captured the mean, right? And the mean is in the center, it's the peak of the distribution. And the reds, this red right there. Do you see that it doesn't even touch the mean? It didn't capture the mean, that's why it's red. Here is another red, okay? Here are two other reds. They're too far away, okay? So statistically, every once in a while, you will get x bar too far away, and even if you construct the margin of error, okay, then it's not going to capture the mean. But these samples are going to be rare. Most of the samples are nicely centered around the mean, and therefore margin of error does actually capture the population mean. Okay, make sense? All right. Okay, one more thing that I wanted to emphasize. All of these calculations that we performed are good and solid only under one assumption, that my distribution, the original distribution that I was looking at, is not horrifyingly bad. And by horrifyingly bad, I mean it should be more or less normal, approximately normal. Okay? So if your population is distributed badly, if it's severely skewed to the right or severely skewed to the left, or it's bimodal or trimodal, okay, something like that will invalidate our analysis. And the reason for that is actually fairly simple. Let me go back. Okay, here, let's say that my distribution is bimodal. All right. So I have let's do this. Okay, that we used before. This is how my distribution looks like. Not normal, right? By any stretch of imagination, not normal. So if I compute the mean for this distribution, it's going to be somewhere around here, correct? That's going to be my mean mu. But is that a really nice representation of numbers in my distribution? No, right? Because if anything, I have a valley in here, right? Very few numbers. Most of my numbers are coming either from the left side of the distribution or from the right side of the distribution. So mean is not a good candidate to characterize the center, okay? So therefore, every time when I try to do the analysis, it's kind of a question mark. Am I using the right technique? Okay? Or how do I interpret my results? Do they make sense at the end of the day? So therefore, one of the assumptions that we're going to use for the hypothesis testing and confidence interval is that the distribution of my sample, which resembles the distribution of the population, should be PDN, pretty darn normal. Okay? So for now, we're not going to, the only thing that we will do is look at the distribution and say, is it normal or is it horrifyingly bad? Okay? And that's how we're going to judge. But later on, during this semester, we will take a look at how to test for normality rigorously. So if I go back This is my sample. What do you think? Is it more or less normal, or is it horrifyingly bad? It's more or less normal, right? There are a couple of things here and there, kind of weird results, right? I have kind of empty spots there, but overall, it looks not bad. It's almost symmetric, right? Unimodal, certainly. Yeah, I have one outlier right there. Yeah, so that's a gentleman, and that probably is the outlier right here. This bar is the outlier, right? So that's gentleman apparently who achieved uncharacteristically high productivity of 551 packages, right? So if we remove that person, probably the shape will change to be even better than this one. So all these considerations, they do apply. Okay, what we just discussed makes sense. We can use the mean, and it's interpretable. Oh, sorry. I need to go back to the slides. Okay, so that's as far as the numbers or means are concerned. Now let's switch gears a little bit, and the remaining 45 minutes or so, let's talk about proportions. Okay, so a lot of data. Oops, I shouldn't do that, right? I forgot not to. Okay. Forgot that I shouldn't switch to the full screen. Hold on. Let me go back. And duplicate. Big changes. Okay. All right. So not all data sets are numbers. A lot of data sets, a lot of data that companies are collecting, they're categories. Male, female, right? Did the customer of the bank default on the loan, or did they not default on the loan? So another example is voting, right? Voting, every time when there is a voting campaign, or voting happens, elections, right? People go into the voting places and cast their votes for Republican or candidate. And the exit polls, they capture these responses, right? Who voted for Republican, who voted for Democrat. So the data that we're capturing is not numbers, right? It's not numerical. So what do we do with this data? We discussed that for numerical, for categorical data, we do not compute the mean, right? Mean is meaningless. As funny as it may sound, meaning is meaningless, right? There is no mean, there is no variance, there is no standard deviation. None of that exists. So the only thing that we can compute are proportions of responses. What percentage of people voted for Republican? What percentage of people voted for Democrat? What percentage of bank customers defaulted on the loan versus not defaulted on the loan? What percentage of people in my sample are males versus females, children versus adults, etc., etc. Right? So therefore, we have to estimate the population proportion. Okay, and oftentimes it's not known. Like when the election's happening, actually we do know at the end of the day what was the true proportion, right? Because when 3 million people, all voters, cast their votes, it takes some time to count them all, right? But at the end of the day, when everything is counted, then we know exactly, precisely who voted, well, how many, we don't know who voted for whom, right? But how many people casted their votes for Republican and for Democrat. So when elections are in place, there is no estimation. It's an exact science, right? So we need the entire population of votes. But there are cases when you can get that. For example, TV stations, right? TV stations, how do they, where do they make money from? TV stations. Commercials. Same thing with radio, right? You air the commercial on the radio. Whoever is listening, they hear that. Whoever is not listening, they don't hear it, right? So can you figure out, for example, what percentage of TV viewers is watching a rerun of Friends on TBS Superstation? What do you need for that? You need to call every single person in the US and ask them, hey, do you watch TBS Superstation? And if yes, then do you watch Friends? Yes or no, right? How much time will it take to call all people? Oh my God, right? Not even try. So therefore, TV companies, they cannot get the exact percentage, right, of TV viewers who tune in on rerun of Friends, right? They can call 2,000 people, maybe 3,000 people, but that's it. So inherently, their process is estimatory, right? It's estimation. That's all they have. Okay, so now let's discuss actually Where's the next slide? Hold on. All right. So what I'm trying to do in these cases is to estimate the actual proportion in the entire population, that number, pi, right? Greek letter that tells me what percentage of my voters, all of them, voted for a Republican candidate, or what percentage of all of my viewers are watching Friends in the evening, right? Now, I don't have that exact number, and I never will, right? But what I can get is a sample, and from the sample, I know the sample size n. I know how many people, what's the count of people who watch Friends. So I can get from 2,000 people sample an idea of what the percentage might be in my big population, right? Now, x is number of successes, right? I call 2,000 people, n, that would be 2,000. X of them, let's say, for example, 252 people, okay? They do watch Friends. So therefore, x divided by n, that gives me the percentage of all viewers who watch Friends, right? Now, x, number of successes out of n trials. That looks a lot like binomial distribution that we discussed, because every time when I call person, my question is, do you watch Friends? Answer is yes or no. That's it, right? So binomial distribution, it's either a success or a failure. And distribution of successes and failures follows the binomial distribution, because it has all the characteristics, right? Every call is either success or a failure, either watch it or not. Calls are independent. The next guy that I call has no idea who I called before, and he doesn't care really, right? He decides for himself if he is watching Friends or not. Now let me show you the binomial distribution, and I'll let you tell me what does it look like to you. So I'm going to switch to probability calculator, and here is my binomial. Now let me get actually, probability of success, let's say 50-50, okay? Half of the viewers, they do watch Friends, and half they do not. And I have big sample, let's say 500, okay? 500 numbers. Maybe not that high, because it's kind of hard to see, right? So let me scale it back to 50. Is that better? Somewhat better. What does that shape look like to you? It looks like a normal distribution, right? So therefore, the rule is if, let me switch back to the slides. The rule is if number of trials times the expected probability of success is greater than 5, or n times 1 minus p, expected probability of the failure, is also greater than 5, then my distribution, here I have actually probability of success 0.3 and number of trials 100. The resulting binomial distribution looks a lot like normal distribution.
So this is like the rule of 5.
That's called rule of 5, exactly right. Yeah, rule of 5. So if n times p greater than 5 and n times 1 minus p is greater than 5, then in this case we can use a normal approximation. Okay? So it's not an exact science again. It's just an approximation. All right? So binomial distribution looks a lot like normal, so therefore we can use a normal distribution. Okay. Now let's take a look at the problem actually, and then I'm going to show you how to compute the confidence interval for the proportions, and then we'll see just how easy it is to do with jump. Okay. All right. So here is the problem. Exit polls. I believe it's called voting problem. The data set is called votes. Right. Let's see. Do I have jump data sets here? Votes. Right. Yep. All right, so let's read the problem first. At exit polls, voters are asked by a certain network if they voted Democrat, and if yes, then they are recorded as ones, or Republican, and if yes, they are recorded as twos. Based on this sample, can the network conclude that the Republican candidate will win the election? And it doesn't really matter, like what you're asking, right? Will the Republican win the election? Yes or no? The opposite will be no or yes, right? If Republican is winning, then for the Democratic, the answer is no. So you can ask the same question for a Democrat, and it's not going to make a difference, right? The difference is if it's above 0.5, that candidate, or if it's below 0.5, right? If it's above 0.5, he's winning the state. Below 0.5, he's losing the state. Okay, so if proportion more than 0.5, we could say that yes, Republican seems to be winning and Democrat seems to be losing. All right, so let's analyze our data, okay? And again, we're going to construct both lower and upper confidence limit. So I'm going to download the votes, just like that. And apparently it's somewhere at the bottom. Yeah, right there. Okay, so here is my jump. I probably need to close out some of the things that I don't need. And FedEx example I'm going to close. Okay, so here are the votes. All right, first of all, what's my sample size? 765. I have polled 765 people who casted their votes already. And you can see that, first of all, what's the data type also? According to this triangle right there. Not triangle, icon next to the vote. It's nominal, right? Nominal data. Okay. So under that, actually, if you double click on any one of them, it will reveal the number behind that. 2 means, according to our classification, what 2 means? Is it Democratic? And Republican? Okay. 2 means Republican, and 1, if you double click, it reveals 1, right? So I have numerical data behind that, but I classify it as nominal data, right? And there are labels attached to 1s and 2s. Okay, cool. Now let's go ahead and actually take a look at breakdown, right? Percentages. So we discussed that nominal data, ordinal data, categorical. The only thing that I can compute are percentages in each category. Well, luckily, there are only 2 categories, right? So let's go to distribution. And I take votes and move them to the columns area. And when I click OK, there it is. Okay. Let me stack it horizontally, just like that. All right, and let's make it bigger. Well, here's my summary of frequencies. It says out of 765 votes, 358 or 0.46797 voted for a Democratic candidate, and 53%, 0.203, voted for Republican. So if I'm going to base my conclusion just on this proportion from my sample, what do I say? Republican seems to be doing better than Democratic candidate, right? So if I would be using my, and this is something called p hat, okay? It's not exact number, right? Not in the entire population, it's just a sample. From the sample, I can compute only point estimate. Remember that? Point estimate, right? A number from your sample is a point estimate. So my point estimate of the percentage voters who picked a Republican candidate is 53.203%. That's the point estimate. How confident I am in this answer? 0, right? So I need to create confidence interval, right? Okay, so let me show you the formulas. They're actually in the PowerPoint slide. Formulas are right here. Okay. First of all, if I have the binomial distribution, which I do, right? This process is governed by the binomial distribution. And it looks like normal. We discussed it, right? Distribution of all samples. Well, first of all, let me actually take a step back and ask you. If I pick another 765 voters, not this sample, but another sample, will I get the same exact proportion? No. It's going to be different, right? So every time when I take another sample, even of the same size, the breakdown of votes is going to be not the same. So therefore, sampling distribution, once again, right? So sampling distribution does not just apply to the sample averages, it applies to the sample proportions, if we're talking about categorical data. So we discussed that binomial distribution looks a lot like normal, and the mean is going to be centered around my actual proportion of answers in the entire population. In this case, true percentage of people who voted for a Republican candidate. And the standard deviation is going to be given by this ugly formula. Okay? P times 1 minus P divided by the square root from n, where n is your sample size. And after that, the confidence interval is very simple. Okay? Just like in the case of continuous data, numerical. X bar is in the center. Here we don't have X bar, here we have P hat, proportion that you compute from your sample. That's your center of the confidence interval. And you go plus or minus, and that part is, what do we call it? Margin of error, right? Margin of error is, this is number of standard deviations that you go to the left and to the right, and that is your standard deviation. Simple, okay? But the difference is, I want to point it out, We use t-distribution for the numerical confidence interval, right? Now we use z-distribution, okay? So that's what statisticians are using. Instead of t, they're using z. Z is what, by the way? Standard normal. Z-distribution is standard normal, okay? All right. So we're going to, again, take two different paths, okay? Path number one would be long and uneasy. And path number two would be how can we do the same exact thing in 2 clicks, quite literally, right? In jump. So let's take first long and uneasy path. So I'll go back to my jump analysis and I'll write things down, right? So specifically we're interested in a Republican candidate. Can we say that the Republican is winning? Based on my point estimate, the answer is yes, it appears that way, because 53.203% so far out of the sample voted for the Republican candidate. So based on my sample, if I didn't know statistics and the fact that I have no confidence in this answer at all, I would say yes, Republican appears to be winning, hands down, no question about it, 53% versus 46, almost 48, almost 47, I'm sorry. So Republican is winning based on this sample. But is he? So let's take a look at confidence interval, right? So 0.53203, that's the number that I should remember, because everything else I can pretty much compute. All right, so let me start a new page right here. So reminder, all the p hats is the proportion from the sample that I compute from the sample, right? All p hats are distributed approximately normally around the actual pi with the standard deviation square root from pi 1 minus pi divided by n, okay? Well, pi is unknown to me, right? Pi is the proportion in the entire population of voters, right? That's if I count everybody, which I didn't. So therefore, we're going to kind of substitute, right? So in order to estimate the standard deviation, or S really, right? In order to make an estimation of the standard deviation, we're going to use my p hat, okay? Square root from p hat, 1 minus p hat divided by n sample size, okay? And my p hat, by the way, p hat, it's all about Republican candidate, right? Republican candidate, if I remember correctly, his p hat was, thank you, 0.53203. Okay. So let's compute the standard deviation, okay? Because we have pretty much, we know everything. Well, what was the sample size, by the way? 765, okay. 765 people. All right, so S is the square root from 0.53203 times 1 minus 0.53203 divided by 765. Well, that I cannot do manually. I have to use Big Fat Calculator, also known as Excel. Okay, so let's go back to Excel. And there it is. So here I'm going to say equals square root, SQRT, right? That's the formula for square root. And I have to put 0.53203 times 1 minus 0.53203, and all of that divided by 765, close the brackets. So that's basically my standard deviation from the sample. And that would be 0.01804, okay? So 0.01804. Is that it? Did I get it correctly? Yes. Okay, good. Well, what do I do now? I compute the margin of error from S. And remember, the margin of error, ME, is Z, not T value, not T score, but Z score, which gives you alpha by 2 in the right tail, multiplied by my standard deviation from the sample. Okay, so Let me illustrate that with the chart. Okay, Z distribution, standard normal, right? So Z, we're going to write it out, is standard normal. Standard normal. Okay? So in other words, Z is normal. Z is distributed normally with the mean of how much? What's the average for the standard normal distribution? 0, that's right. And the standard deviation sigma is 1, that's right. So here's my 1, and here is the normal shape around the 1. So here's the 1. Okay, so if I want to be, let's again take the same approach as we did before in the previous problem. Let's take 95% confidence level, right? I want to be 95% sure in my result. So 1 minus alpha is 0.95. So therefore, alpha, your significance level is 0.05. And therefore, no, that is 0. Therefore, what do I do to find my Z values? Well, I have to find symmetric values on the right and on the left, such that in between these values I have 0.95 area. And outside these limits I have the rest of that, 0.05, but it's left and right tail, so therefore on the right I have 0.025, and on the left I have 0.025 as well, right? And again, it's going to be approximately how many standard deviations? 95%. 2 standard deviations. So my Z value should be close to 2, right? It's not going to be exactly 2, but that's kind of our self-check, right? We need to remember to compare it against 2, and if it's too far away, we know something went wrong, right? So let's find the, so I'm looking for Z, right here, right? That Z, let me start a new one. I'm looking for Z with the subscript 0.025. That gives me 2.5% in the right tail of the distribution, correct? So let's go back to jump. There it is. And actually, I need to call up again the probability distribution calculator, right? Help, sample data, and examples, teaching scripts, I'm sorry, interactive teaching modules, and distribution calculator. And I don't have, I believe, a standard normal in this list, but do I need standard normal? No, because standard normal is still normal, right? It's just the mean is 0 and standard deviation is 1. It's there already, actually. Okay. So what am I looking for? Values or the probabilities? Values, right? Given the right tail probability. So input probability and calculate the value. And again, 2-tail probability or just the right tail doesn't matter. Let's do the 2-tail. 0.05 in 2 tails. 1.96. Does it come with our intuition that it should be close to 2? Yeah, it does, right? Close to 2. Not exactly, because it's not. It's all estimation.
So when would like 1.96? What would like classify as not close enough?
Oh, not close enough to 2?
Correct.
I don't know. This is just informal test. If you get 1.5, you can say, "Oopsie, something went wrong."
Like 1.8.
1.8 would be probably yes. Close enough. Yeah. So it's not a rigorous test. I'm just checking to see if what I intuitively understand should happen, if it's indeed happening. So it's kind of statistics. Once you get into the spirit of Christmas, so to speak, once you get enough, statistics done, you develop intuition, and that's what I want you to develop. Think about, business phenomena or problems in statistical terms. That there is a distribution. If you cut off the right tail, that's approximately what it should give me, and then you do the exact computations using the software, and it just confirms your kind of gut level feeling. That means that you understand statistical nature of everything that's going on. Okay, so 0.196 is close enough, right? Okay, so let's go back. So this is the Z that I want to use, right? 1.96. Okay, cool. Now let's compute the margin of error, ME, margin of error, and that would be Z times the standard deviation, right? So 1.96 times, oh God, what was the standard deviation? 0.018 something something. 0.04. Okay, so this is what my margin of error is going to look like. Correct? So where this number is coming from, we just computed that. So let me go to the recent notes. Right? And that's it. Yeah. So this is my standard deviation from the sample. Okay. That's the number that we just computed before. So margin of error is simply take the z-value, which we found using the normal standard normal, and multiply it by the standard deviation. So again, it tells you how many standard deviations to go to the right and to the left to get the upper and lower confidence limits, right? And that's it pretty much. Okay, where do I go? Yeah, margin of error right there. Okay, so let's compute that numerically. And for that I need Excel again, right? So let me go back to Excel. Here is my standard deviation, and 1.96 is my z-value. So therefore my margin of error is equal to my z-value multiplied by the standard deviation from the sample. So I'm getting 0.035359. Let me write that down before I forget. 0.035359. Okay? And after that, I can compute my upper and lower confidence limits. And just by analogy with my previous problem about FedEx and workers' average productivity, in the middle of my confidence interval, I have the point estimate. And that would be my p hat, right? P hat. And I have to add or subtract the margin of error. And that would be what was my p hat? 0.53203, right? That was my estimate from the sample, what percentage of voters will pick Republican candidate, right? And I have to go up or down, this margin of error, 0.035359, okay? So let's compute upper confidence limit and lower confidence limit in Excel. All right, so here's my margin of error. Here's my p hat, 0.53203, and my upper confidence limit and lower confidence limit are actually, I take p hat plus margin of error that gives me the upper, 0.56, 56%, that's my upper estimation, and my lower estimation is p hat, subtract the margin of error. That's my lower estimation. So 0.5673 and 0.4966. 0.5673 and 0.4966, right? Okay, so once again, we have to ask ourselves a question, right? Well, what we're trying to estimate is actual percentage of people in the entire population of voters, right? Everybody who will come to voting places, right? That will vote for a Republican candidate. That's what we were trying to estimate. Okay? The best thing that we had is p hat, which is right here. And from the p hat we said, it certainly looks like Republican is winning, right? Because p hat tells us he gets 53%. Now that we know the estimate, and by the way, what's the meaning of this thing? We say that whatever the actual proportion of people that will vote for a Republican candidate, we don't know it yet, because it's only a sample, but with 95% confidence, I can conclude that it's going to be somewhere between 49.66% and 56.73%, right? So, can we conclude that the Republican is winning? Again, no, right? Because here is your picture. 0.5 is my holy grail, right? That's the divider between winning and losing. So my p hat was right here. It was approximately 53%, right? When I became 95% confident, my p hat basically gave me, here's my upper confidence limit, approximately 57%, right? And here is my lower confidence limit, LCL, which is 49.66%, right? So it's just slightly below my 0.5, but it is still slightly below. It is still below, right? So this portion of my confidence interval says, yep, he's probably winning. This portion of my confidence interval says, well, it might be that it's not quite right yet. It's not quite clear. Okay, he might be also losing. So both the possibilities of winning and losing are included in my confidence interval right now. So again, it's indecisive, inconclusive sample.
So since it was 0.4966, let's say it was like 0.51.
Mm-hmm.
Since the p-hat is still in the middle, is it still considered a p-posted?
So this one, you're saying 0.501, something like that, right?
Well, I mean, let's say the LCL was 0.51.
LCL point.
And the UCL stays the same.
Yeah, upper stays the same, but UCL goes above, right?
Correct.
So in other words, it's on the other side of the fence now, right?
Yeah.
Then you're saying that, hey, all of my confidence interval is now on one side of the fence, and it's all above my target of 0.5. So therefore, I'm 95% confident that my true population mean is somewhere here, and the entire confidence interval is above, so 95% confident that the resulting proportion is going to be more than 0.5. So that gives me 95% assurance that probably he's winning. But there is still a teeny tiny possibility that even then it's actually not going to happen, right? But 95% is good enough, so we're going to say likely he's winning. But now that we have this number, 0.4966, can't even say that, right? Both opportunities are included in the confidence interval. So that was the long way how to construct upper and lower limit. And that's how you're supposed to do your homework. Problem number 2, okay? Now let's see how JUMP does that in easier and more straightforward way, right? So I'm going to go back to my analysis. Okay? And let's take a look at the votes right here. Do you see where I should go? Confidence interval. So confidence interval, and I have few options, right? We discussed that default confidence levels in statistics, default, the standard is 95% confidence, 5% significance. Two other possibilities include a rigorous test, right, with 99% confidence and 1% probability of error, significance, and a kind of a relaxed test, right, not so rigorous, 90% confidence. So if I want to be 99, oh, by the way, good question. What will happen with my confidence interval if I go from 95 right now to 99? It will become wider or smaller? Wider, right? We discussed that today. When you become more confident, your confidence interval becomes wider. It includes more possibilities. If you become less confident, it shrinks. And in the limit of 0 confidence, it becomes just 1 point, right? Well, let's see, 0.99. We had, 0.95. Let's show 0.95 first, to verify if what we did actually is correct. Are these the same numbers? Can't quite remember what we had before. Lower, we're looking for Republican, right? Republican candidate. And here's my lower confidence interval, and here's my upper confidence. So my lower, if I remember correctly, was 0.4966. So here it says 0.49659. That's your 466, right? And upper was 0.5, oh gosh. 673? Yep, 5673. And here's your 0.5671. So the difference is in the 4th decimal. Okay. So if you want to do something, funky, such as I don't like these standard choices. I want to be 93% confident for whatever reason. Some weird choice, right? You can certainly do that. 0.93. Click OK, and it will update. No, it will give you a different version. And still, if you're looking at Republican, that's your lower boundary and that's your upper boundary. So, very straightforward with JUMP, but you need to go through this exercise at least once manually just to see how it works. And that's actually a nice way to check yourself, right? When you're doing the homework problem, once you're done with your computations, it's a good idea to run this thing in JUMP and see if you're getting the same result. And if your results are vastly different, you're going to say, oh, wow, something went wrong. Let me check my math. Maybe I'm using different value of z. I didn't quite get it right. Maybe there is an error in standard deviation computation. Okay? Make sense? Any questions, concerns, complaints, sarcastic comments. All right. So this is it for today, right? We're pretty much done. Okay, so in the next class we will discuss homework, obviously, and also we'll start talking about hypothesis testing. And for the rest of this semester, pretty much what we're going to be doing is hypothesis testing in all different forms, shapes, and sizes. Okay?